Hi, I'm glad to share with you our work learning to simulate vehicle trajectories from demonstrations. This work was done by members from Penn State University, Washington University, as well as Tehran Intelligence. In many fields such as transportation and urban computing, policy research has been attracting more and more attention in the community. For example, researchers seek to develop intelligent signal control policies to help reduce urban traffic jam, and taxi order dispatching algorithm is developed to optimize the taxi assignment when users are using their phone booking taxi driver online. Building or testing these policies based on real world environment is actually very low efficient and usually cost a lot. So researchers usually employs a traffic simulator to train and test the policy. A traffic simulator, as defined, is a virtual environment that simulates the real world traffic, including the interactions between vehicles and the reactions to various traffic environments such as road network and traffic signals. Just like in some video games that we're all familiar with, we build a virtual world that is parallel to the real one, allowing us to test all our kinds of constructed construction policies freely and virtually. In transportation, microscopic traffic simulation plays an important role in planning, discussing, and operating of transportation system. Also, it is convenient for the simulator to generate a large number of simulated data that enables the training of the intelligent controller. After our policy based on the virtual simulator is trained, we need to apply these learned policy in real world traffic. But the problem is sometimes it's not very practical and even risky to directly apply our policy learned in the simulator to the real world because the real world is a lot more complex and different from the simulator. In the field of transportation, currently there are several popular simulators, such as Sumo, IMSUM, and MIDSUM. The common feature for these simulators is that the simulation of the vehicle movement are all based on some certain physical or empirical equations that describe the kinetic movement of vehicles. They are known as the car following models. For example, the cross model is one of the most commonly used car following models. It employs several equations to calculate the current safety speed and desired speed for the vehicle to follow in the next time step. But these car following models simply have some drawbacks. For example, simple models actually do not really reflect the real world vehicle behavior. And secondly, fixed physical models usually needs calibration. It makes them very hard to adapt to various real world traffic environment. Now we know that it is critical to build a simulation system that is close enough to the real world traffic. But how can we do it? Actually, a natural consideration would be to directly learn the vehicle's behavior from the real world trajectory or traffic data. The simulation is supposed to be more lifelike and natural by learning from the real traffic records directly than handcrafted rules for those vehicles' movement. So our proposal here is to learn to simulate, which means learning from the real world demonstration data. Here's the problem formulation. Instead of reading to you, our main goal here is to recover the driving policy for each vehicle from the given expert demonstrations, i.e., their trajectory data and real world traffic. Mathematically, the objective is to maximize the log probability of generating trajectory tau m given that the the vehicle M is following the policy pi m. Here, each trajectory is a sequence of states and actions, where t is a local time span. The skeleton of our method is shown as follows. We actually assumes that all drivers are sharing a homogeneous policy pi, but with very different observations or state. Each vehicle, therefore, yields very different actions. State S is defined as a set of features that are selected to describe the current observations, including road network, traffic signal, and speed or position of current vehicle and front vehicle. Action A is defined as the speed of the vehicle in the next time step. In this paper, we're using the generative adversarial imitation learning as the learning model for our simulation system. This framework attempts to treat the original optimization problem we talked about in the previous slide as the generative adversarial network. This network alternates between 1, the discriminating step, where the discriminator classifies each trajectory as either expert trajectory or generative trajectory, and second, generating step, where the generator updates their policy to adversarially confuse the discriminator. When training the discriminator, the generator serves as a fixed policy and rollouts of trajectories. The discriminator takes both generated and expert trajectories as input and tries to distinguish between them. At the same time, when training the generator, the learned score function is used as a cost to help update the optimal policy. The two networks, discriminator and generator, adversarially plays a game and get optimized in each iteration alternatively until the generator is able to generate good enough trajectories to fool the discriminator. In our experiment, we're using two kinds of real-world road network and traffic records from Hangzhou, China, and Los Angeles, US, as a dataset to train and test our model. The Hangzhou dataset contains a 4x4 network and several other separated single intersection network. The Los Angeles dataset contains a 4x1 arterial road network. We use the root mean square error, short as RMSE, as the metric to evaluate the error between the real trajectory of vehicles and the trajectory recovered by the learned policy. For comparison, our baseline methods include conventional car following models such as CFMRS, and CFMTS. We also compare our proposed model with a well-known imitation learning method, behavioral cloning, short as BC. The experiment results clearly shows that our method outperforms both conventional methods and the baseline learning methods. Besides the traffic simulation learning work, we have other works in reinforcement learning-based traffic signal control. Please follow our recent approaches by scanning the following code. Thank you for your time.